¿Por qué va a salir fuera? Madre mía. Pues salí fuera del todo, yo pensaba que era por si la puerta estaba cerrada. Pues tenemos que esperar. No.
Ya me has dicho. Hay dos opciones, o te quitas de cámara, que siga grabando.
No, pero te quito de cámara.
Quita el audio. Quita el audio.
Vamos a empezar. Good afternoon, everyone. Buenas tardes. Today we have a new talk on the cycle data science, Patricia Roman. It's for me a great honor to introduce Professor Marc Leman. Marc Leman is Methuselah Research Professor in Systematic Musicology, Director of the Institute of Psychoacoustic and Electronic Music, Head of the Department of Art History, Musicology and Theatre Studies of Ghent University. He founded the very important and innovative Art and Science Interaction Lab. His research and teaching is about music interaction and technology, and he has an excellent and truly impressive teaching and research record. He has more than 400 publications, the majority in papers in high impact journals, and he has supervised a high number of doctoral theses. As a result of this extensive experience, he has also received many prestigious awards in his research area. Actually, we are both supervising the PhD thesis of our student, Marc Vidal, who is also here in Granada at our department developing and stay. This is a really interesting data-driven project with contribution, methodological and theoretical contribution in statistics to solve problems in musicology and neuroscience. And well, I think Professor Leman can explain it better than me. So, thank you, Marc, for coming to Granada, to our university. Please, you can begin.
Thank you very much for your nice introduction and for inviting me these days in Granada for the interesting talks with the people, and also for giving this talk. It's a kind of experiment also for me, because it's challenging to speak about interdisciplinary matters, as you all know. But this is an opportunity really to confront my research with your interests and see if there is a match and possible future interest. As you heard, I'm coming from the humanities, but I introduced this term in my faculty because I believe that, well, first of all, the humanities, they typically have a focus on cultural values and meanings, and how people construct meanings in order to make their life interesting. I think that's a very valuable question. However, in augmented humanities, we want to steal, let's say, methods from other sciences, statistics as well, and maybe physics and other sciences, to enrich what we can say about this human research question. And so this is the notion of augmented humanities, is an enriched humanities. where we do use empirical methods and data analysis and become, let's say, more scientific than just producing narratives. That's a bit the idea. And interestingly, there are many colleagues that actually are willing to do this. People from archaeology, they work together with the geographists and so on, and biologists. People from my department in old paintings, they work together with people from chemistry and so on. So there is a huge interest in this development. But of course, we also have to think very carefully about, okay, which data do we want, what kind of data analysis. And so what I want to say today basically is that if we do such an analysis, for example, if we apply statistics to our data, it's very important to understand what we want. And to understand that, we need a good knowledge of the theoretical concepts and also really focus on the research. So our focus now in our department is on monitoring and then on analysis. We also even have a focus on applications where we apply the notion of biofeedback in order to produce what we believe are interesting applications with music as the center. Music for us is still the central thing. All the things that are written here will be demonstrated in the examples that I give. Okay, this is a view on the lab that we have, and this is a typical setup, I would say. So we have a musician producing music, and then we have researchers sitting here recording. Once you have the data, you can start doing the analysis. The lab infrastructure we have at this moment, this is let's say a schematic, but we have inside arrays of speakers. We have about 80 speakers or more, where we can do audio rendering, three-dimensional audio rendering. We have 16 infrared cameras to do recording of human movements with markers that we put on it. And so there is infrared light shining on it. These markers contain mirrors. They reflect the light. These are picked up by the cameras, and so we can reconstruct the 3D models. We have a huge projection screen. We have EEG caps to measure sensors, all kinds of sensors. And all this is, let's say, controlled from a central clock that we have that actually drives all the other devices that we have. We have a considerable storage capacity in the lab, but during the night, the entire recorded data is streamed to about 6 kilometers from our center. Is another campus of the university, where everything is stored on large servers, and where it can be accessed for analysis later on. This is what we have. So the building is that one. Is also, there's also a library, a public library from the city, but the university has the 4th level, and also we are downstairs at the -2 of this building. And there is a connection with a fiber ring to cultural centers. So the idea is to be able to do, let's say, virtual reality things and on different places. And this is the engineering tower where the things are stored outside the center of Ghent. So this is a bit the context that we have. The lab was actually fully operational only since about 2 or 3 years. We planned it maybe already 15 years ago that we should have this lab, and now we have finally we have the lab. So we spent a lot of time before in actually doing measurements and synchronizing everything. Now this is arranged, so now the focus is more on the data analysis and the statistics that we can do for that. So in my talk I will handle these three things. I will first go a little bit deeper on the theoretical assumptions that we have, and then I show examples of three recent studies, and then the applications in the field of biofeedback sports, and the last one is an ongoing research activity that we do. So first of all, the research question and the theories. This can be summarized in one sentence, which is a bit complicated in itself, but nevertheless it gives an idea. The idea is that music is a tool, or let's say a signal, or is something. It is music that allows humans to engage and to have actions that are enriching for the human who does it. That's the idea. And this gives empowering effects. And listening to music is what we would call the passive thing, but we have much more actively engaging things like dancing to the music, right? Or playing music yourself. This always requires an effort in synchronization, in the use of sensory motor capabilities. These are very time-critical things that you have to do as a musician when you engage with the music. And so, so the hypothesis is when you do this, this generates empowering effects. Okay, you will ask me, okay, what are these empowering effects? Well, that's what we have to investigate also, but we think it makes you stronger as a person. It makes you more alert, more active, more in control of the thing. So it raises the level of, let's say, your being in the world around us. I have three basic theories that allows us to have a perspective on it. So the first one is called embodiment. Embodiment means that humans use their body, their movements, their actions for making music, but also for, we call that coding, encoding the music, but also for decoding the music, for understanding what music means. We strongly believe that people somehow mirror movements that are implied in the music. They mirror the movements in the actions, in the repertoire of actions. And due to that, they can actually feel the music as if they produce this music themselves. And this is a very strong and important hypothesis. And so syncing, so many people tap even without knowing that they tap, is already part of such an action, but moving along with the music that you hear, and empathic gesturing is really also, let's say, speak with your emotions in relation to the music. The second theory is more a modern brain theory, which says that the brain is not, as we thought before, just to make a representation of the world. No, it is actually a predictive engine. It constantly produces predictions. And if what you predict is not corresponding with with the data that come in, you have a prediction error, and the prediction is adapted in the brain. And so, for music, it's very important that people, when you ask people to tap to the music, they will typically tap before the actually tick of the music, before the beat of the music, or before the tick of a metronome. They will tap 25 milliseconds before. So that means that they have engaged a predictive engine that somehow knows how to cope with lower delays due to your arm, and short delay due to the tick that you hear. But to synchronize it in the brain, you have to tap before. And the last one is often the most difficult, maybe sometimes to explain. It's about expression. This is a difficult concept, but you can easily understand it from a Darwinian approach. Darwin studied animals, right? And for Darwin, the expression that I have is actually, when I express myself, it's actually meant to have an impact on you, and you express to have an impact on me. And so we have mutual exchange of expression, and due to that, we can establish a level of interaction. Okay, so that's, and that is very, that is also engaging your emotion. So these are the three theories that we have. We have the body, we have the prediction, and we have the emotional system. That brings it, and the difficulty is that, yeah, we have to deal with all these things together very often. So the first example that I have is the publication of a very recent study of 10 May this month in Computers and Human Behavior. And in this study, the goal was to play along with an avatar, so to develop a new kind of play-along device. You know, musicians, they learn, for example, jazz musicians, they often play, and they play along with a combo that is doing the written section, yeah, and you have a saxophonist playing with a music playback system. But here we had musicians from an orchestra, and the task was to play along with the principal violinist of the section, so that you have the same movements. If you play in an orchestra, everything should be synchronized. So it's a kind of play-along system, and we do it with a 2D avatar and with a 3D avatar. And the question was, show that there is a difference maybe between these two avatar types in learning and in playing. So, but instead of trying to define quality of playing as an abstract thing, we developed a method to compare the avatar player with the human player, and to do a comparison of time series that they produce. You could see it like this. This is the setup for constructing the avatar. So this is the principal violinist of the orchestra, equipped with a mocap suit. This is what comes out of the motion caption system, and then this is an avatar constructed. The avatar 2D is like it is projected on the screen. The 3D avatar, you can walk around, and in both cases you wear HoloLenses. So just to give an example, this is, I don't know if it will be very clear, but this is the setup a bit. So you have a HoloLens, and you see this. Now, through the glasses, you see the avatar on the screen. And now you can scroll forward and background and play along with it. Okay, and in this case it's the same, but the avatar is now in 3D. and you can walk around it. So, yeah, okay, you see the avatar is not perfect, but okay, it's difficult to make it like this. Okay, and just I mentioned two concepts because they will appear in the next slides. So I will speak about the frog. It's that place at the bow, that's the frog. And we also have the bridge here, the bridge. And so the bow, when the bow touches the strings, there is a distance to the bridge, and also there is a distance to the frog, where your bow is on the violin. And so this is an example of the data over time that we see, but these are typically angles like the wrist of holding the bow, the elbow, the shoulders. But what I will show is basically this is the bow position relative to the frog, right? So you have the strings here, and so this is this distance, right? And this is the bow position relative to the bridge, so this is this distance. And so the task is, show us that the two players fit, that there is a synchronization, that everything fits. This is not such an easy task. Fortunately, we had my PhD student himself he is a contrabass player, but so he knows how to play violin, and he did much of the pre-processing here. And the idea was to focus on bow strokes as events. So rather than just taking into account the time series as it evolves over time, we work with events that are defined by bow strokes each time. So the red part is this is bow position on top. This is the loudness, the second graph here. And on the right, you see an enlargement of the red square, and you see the bow strokes of the of the avatar and the subject violinist. And here we see the distance from the frog related to the distance to the bridge. So we see that distance between the avatar, the principal violinist, and another violinist. And then we try to match them using Procustus analysis. So this is associated with a particular cost, and that cost is actually the thing that we want to have. This is a metric. We tried 50 different metrics, but we retained only 2 of them, which was this Procustus metric, and the other metric is called the spark index. Spark index is a measure of the fluency of the movement. You can interpret it like this. And so with these 2 things, then we explored the analysis, which would look like this for 6 different players, but those players on top play in the condition that they see the 2D avatar, and those below play in the condition that they see the 3D avatar, but they all play the same piece of music. And here the metric is the Procustus. So So we take, let's say, over time, we take the mean of the blue one is one particular player, and the red one is actually the mean over all the players. And so if we then compare, for example, the blue line with respect to the red line, we would obtain such a graph like we have here. And in the end, we get data like here. But what we finally want to show is that also over time, for different trials, you could call them repeated measures if you want, they show that the 3D avatar here is, this is Procustus, so the green is the 3D avatar and the red is the 2D avatar. So we see a learning effect of the two-dimensional, in a two-dimensional condition. We don't see a learning effect in the three-dimensional condition because it is already better and there is not much place to learn in that case over time. So that was our conclusion. With respect to the Spark index, you are better when you are on top. So also there we see that the 3D avatar actually allows you to produce more fluent movements, but we don't see anything over time that is related to a learning effect. So this is a typical kind of, as you see, pre-processing part, signal conditioning, and then feature extraction, and then try to show that there is a learning effect and that we have a difference between the two conditions. This formed part of a European project that is still ongoing. So our task was to show that we can compare situations, because in the end we want to compare players that have robotic equipment. And so the goal of this project is to show that there can be an exchange of information through haptic sensing. So normally we have visual contact, we have auditory contact, but in this case there is also contact with robotic arms that allow you to send information from your movements to the other person. For example, a teacher violin to a student violin that receives that information and also plays violin. And so that's what we do now. This is the first time that I can show this, because this was had to be patented first by the companies that developed this. But if you look carefully, you see two girls playing the violin, but they have a robot arm. Maybe I can show it. Okay, and so that's the teacher is on that side. And so one application could be that you learn to play violin and you have a playback system, and at home you wear a robot arm, and the playback system also contains information that guides your movements while playing. Will that ever happen? I don't know, maybe 10, 20 years from here, or maybe never. But in any case, this technology is very useful also in physiotherapy, for example, in medical centers, clinical centers like this. That's also why we do it. My second example is about classical ballet. It's also recently published, and here the goal is to show anticipatory behavior of dancers. I can show you. I go quickly over it. But this is the dance. Do you hear it? Huh? Yeah? Okay, and then we ask ballerinas to come to the lab, and we make this kind of recordings. such a recording, as very often now, my students do overkill of data gathering, because in the end, what we did is just follow one single marker, which is on the heel here, on the heel, and just to see if it goes up and down. All the others are not yet studied, but it would be very complicated to study how they are actually correlated over time and so. But in order to do that, you need a very good research question. And so we have a very good research question for one marker, but not for all of them, unfortunately. So, but for one marker. And so the research question is to see how it anticipates, how the movement, to what extent does the movement anticipate the beat of the music. Because that gives us an indication of the control of the dancer in expressing herself. So first thing is that we studied actually in this musical excerpt there are two fragments. You see fragment 1 and fragment 2, and they are in between. There is also some music, but these are the two fragments in the thing. And this is the same fragment but isolated. And so the dancers had to dance this. We only had 4 dancers, very limited, but they had to dance it 12 times. So we have a repeated measure here. This is very typical for our data. We have a lot of data, but not many students, not many subjects, very few actually. So we have very few data actually, although we have a lot of data. That's a bit the challenge here. And so here the green is when the heels are up, and when the heels are down, it's red. Very important because it will come back in other examples that I give. The vertical. So these are the 3 subjects that we see here. But the vertical axis is phase. Right, so it's the timing. So if this is one beat of the music, and this is the next beat of the music, and your step, your heel is touching the ground here, then you have completed almost the cycle, right? And so we represent that as phase, right? And so it is between 0 and 2 pi, or if you shift the axis between minus pi and plus pi, but the vertical axis is a circular axis. So all the statistics we do is with circular response values. And then we expanded this over time. So now you see all the subjects together, the 3 subjects together, and this is time from 0 to 15 seconds for the first fragment, and 0 to about 12 seconds for the second fragment. So now the interesting things pop up. It is that, and this is the first fragment in isolation. So you see that there is some kind of effect of context in anticipating, because we are below 0, so that means everything that is below 0 is actually anticipated. The heels up moment comes before the beat of the music. So this is how it actually relates to the music. You see easily that this part of the music is identical to this part, so there is a repetition of the context. And interestingly, due to that repetition, people use their sensory motoric memory for that, and they are going to anticipate a little bit more. And we know that they do that without being aware of it. It's a subconsciousness phenomenon. that we see here. I think it's for the first time that we were able to show an effect of context in the sensory motor behavior that similar to tapping or to that kind of research. So this is something very intriguing, actually. And I go now to the third study, which is about tapping, which is also, I think it's going to be published one of these days, very soon in the end. It's a bit complicated, but I explain. The figures are a bit complicated, but we have 4 conditions. And there are 2 people, 2 subjects sitting together, and sometimes they see each other. So when they see each other, that means that they are coupled. When they don't see each other, there is a wall here in between, they are uncoupled. But when they are coupled, they can see the arm of the other ticking from that perspective, from what we call a second person perspective. You see the other one as a second person. But there is a condition where you see the arm of the other ticking from your own perspective. We do that with virtual reality glasses. So somebody ticks, it's not your arm that you see, but it's the arm of the other person. So in that case, it would be the one PC, it would be, so you are coupled, it's the arm of the other person that you see, but it's from a first person perspective. That person, her arm, is seen from my viewpoint. And so the task here is a task in what we call entrainment. Is this connected tapping, is this exerting an influence on one of the other? Because one subject taps with a metronome, let's say at 600 millisecond interval, and the other taps with a metronome at 610 milliseconds interval. So that means that the metronomes are dephased. They are like this. You start. And then it starts again. So you are dephased, and you are asked, follow the metronome that you hear in your headphones. But you see the other ticking at another speed. So the question is, to what extent are you influenced by this? Okay. This is the kind of data that we get from it. The structure is very simple. We have time, and then we have the indicators, whether it is subject 1, whether it is metronome 1, that produces a tick at that moment, or whether it is metronome 2 or subject 2. And so the data over time, you see 10 cycles in total. It takes 400 seconds, is that possible? Yes, I guess. Of two subjects, gray and kind of yellow. And the second panel is where we fold the 10 cycles to one single cycle. So then you see that, and the vertical axis here is now what we call the relative phase. It is the time difference between a person tapping and the person's own metronome. We do that for the 2 subjects, right? So it's this formula that is applied for that. And you see, if you deviate from 0, that means that there is an influence is going on. If you are below 0, you see that almost all the dots are below 0. That means that they are anticipating. So they are anticipating their own metronome tick, but they are at the same time influenced also by what the other is doing. And so the question is, okay, try to understand what is happening here. If we look just at the intervals that they produce while tapping, you see that nothing can be said because time is not taken into consideration, and so there is no real difference here. So the first type of analysis that was done was with recurrence analysis. I don't go deeper into it, but you could interpret this as an attractor landscape. Basically, according to me, it shows the instantaneous frequency of one cycle going from 0 to 2 pi. And you see that the coupled conditions, the 2p coupled and the 1p coupled, so these two curves, they show this clearly this deviation in the instantaneous frequency, which is due to the influence by the other. But I did another analysis a bit different from this, the usual, because it's circular, you need to use a von Mises mapping to get it to the face, and then it's with splines. And here you see the 2PC is the coupled condition with the second person, and the coupled condition with the second person as your own arm. And this is again the relative phase that we see here. I was very much intrigued by the asymmetry in this thing. And it's quite hard to understand why there would be an asymmetry with respect to the anti-phase moment. So apparently the crossing shifts to the right, and also with respect to in the horizontal axis you also see asymmetries. Why? Okay. I think that these methods do not really provide an answer, according to me, because they are descriptive. They don't go into the causality of the system. And that was the reason for me to explore a bit further as an amateur, I would say, in these matters, to think about a constellation where we could represent the entire experiment with oscillators. Of course, the metronome is really an oscillator. The tapping could also be seen as an oscillator. And so you have the two subjects and their own metronome, and the two subjects see each other. So we can define parameters here. One parameter is the coupling parameter. Either you are coupled to your own metronome or you are coupled to your subject in a kind of connected way like this, right? But you can also tap earlier than your own metronome, but still stay very much coupled. So therefore we have a second time delay parameter also. So we have coupling strength, that's the K, and the time delay is the D parameter. And so the connection can be described like this. So the omega Y is the eigenfrequency of the metronomes. Okay, that is inherited by the subjects because they have to follow that. And then the whole thing, the whole dynamics is based on prediction error correction. So you correct, so to speak, your frequency due to what you see with the other, and time delays can be taken into account. So, okay. And so what comes out of this is then this kind of graph where we have the four conditions. I use the uncoupled conditions. I use the same system, of course, but they are not connected, but I leave it as it is for the moment. And still the system produces those higher dots, so that means coupling. This is coupling to the own metronome. So now we can express each subject in terms of the coupling parameters. I only have 6 or maybe 5. I can actually do the whole thing with 5 parameters that have a physical meaning now. And they allow me to understand the dynamics. So here I take away the variance of the cycles and subjects, and here I give that variance into the data. So what happens here, I'm not yet very clear, but probably it's, yeah, it could be an artifact, or because we did not have that many subjects, only 19 couples. So this is the setup of now what I have so far done. So I have an OD system that I test. I can define my coupling parameters and my delays myself. I can reproduce phase functions. I can reproduce simulated data with noise. And then I can send this to the regression, and then I get out the posterior distributions and posterior predictions, and I compare them with the original just to check the model. If that works, I apply the model to human data tapping, and I get out results like this. For example, these are results of these are the posterior predictions. So the dots are the data, and the continuous lines are the predictions of the model. And we can do that for each individual and for each cycle. It's very deep. We can go really very much in detail here. And I also developed a tool, thanks to Marc, who set me on the way how to do this, where I just can control all the knobs, and the thing shows me the curves and gives us a really understanding of what happened with the asymmetries in the original curves that we saw. And even the thing predicts what would come out in an attractor, a landscape, a recurrence analysis. And it even goes further, because we also get, if you see these deviations, these are instantaneous periods or frequencies. They predict what we will find in the brain, because there we had a study with what we call frequency tagging. That means that when you hear a frequency or you tap a frequency, there is a component emerging in the brain that actually follows that frequency. And so with electrodes, you can make a recording of that.
No hay solo pantalla ni nada, se ha ido al fondo.
Maybe was it computer?
Hay un cable que se da.
El HDMI no lo está viendo, está poniendo, la pizarra pone que no encuentra el HDMI.
Se apaga su ordenador.
Ahí se afloja.
Se apaga su ordenador.
Pero dice
Se apaga su ordenador.
¿No se apaga el ordenador? ¿Mal? Se apaga el ordenador. Sí.
Ya no encuentra el HDMI.
Pero se ha suspendido solo.
Es que estaba más conectado.
¿Dónde tiene puesto una hora de suspensión?
Okay, sorry for this small technical problem. So, but yeah, this is what I wanted to say, that we generated also with this a hypothesis about what we believe we will find in the brain due to this kind of analysis method. But I must confess, this is for us very experimental, and I think for you it's all common knowledge, but I think there at that level a good match would be possible. Putting it all together, and this is very much also the context in which Marc is actually doing his PhD, we believe that due to music, the humans are engaged in prediction, embodiment, and expression. These are processes connected with emotional processes also, and this generates particular activation of neurotransmitters and hormones also that gets established in the system. And due to that engagement, you get some feeling of pleasantness, so it gives you a reward. And so that reward says that, oh, I want more music. And so this is a kind of addiction to music that you develop. Of course, it's a very soft kind of drug addiction that you get with music, but it is based on the same principles of drug addiction in the end. And what Marc is studying is very much the relationship between these two levels with pupillometry and with EEG. Finally, I will show you very quickly application, because what we believe is that the insights that we want to get can be used in biofeedback systems. Okay? If we understand the perception-action couplings, we can use it for applications, typically that would be music-based biofeedback applications. We have one very successful application in sports, but our goal is to develop this also with brain scientists. So that would be music-based, brain-based biofeedback. Okay, and the role of biofeedback is always to retrain, to relearn your habits, to retrain how you run, for example, to retrain the fact that you have a depression, to come out of that depression. That would be one of the applications of such an approach. In this case, it is a running, and the goal is to do injury prevention. So runners, many of them have bad style because they run on the heels. They come down on the heels. It's much better if you come down on the tip of the foot, because then you have a much softer landing, less impactful on the knee. And so this is a device that does it. So here with this accelerometer, we measure actually the impact of the foot on the ground. And this is connected with the system. You listen to music. If the impact is too high, you get noise. Noise together with music, that's not very pleasant. If you change your running style, you get less noise, then you get music. That's very pleasant. So we apply a Pavlov punishment approach. Actually, Pavlovian approach. So punishment and rewards are the two things that, and surprisingly enough, it works very well. But we have been working many years on that. So this is, I think, a video from about.
Depuis 2007, le département de musicologie de l'université de Gand se penche sur la question, réalisant différentes expériences. Aujourd'hui, dans le hall des sports, les chercheurs tentent de voir si le rythme de la musique modifie celui du coureur. Le tempo de la musique entraîne le coureur, et donc il va adapter le rythme de sa course à la mesure.
Okay, this is another.
Dans le cadre du programme européen,
Okay, this is another one.
muziek heeft een enorme impact op de mens, ook tijdens het sporten. De afdeling muzikologie van de Universiteit Gent onderzocht op het tempo van...
Okay. Like this to see effects in many people. This is an example of how long it often takes. So some research in 1997 to 2009, up to now, this year yes, a spin-off company in this field. And so the biofeedback could be summarized like this, but it is mainly what I explained already. And the effect size is really quite large. The effect size is about minus 26%, which is a huge effect size in statistics, I would say. Very often it's much smaller. But here, yeah, this was done by the sport science faculty. So to end my talk, I will speak very briefly about a new study. It is not related to biofeedback, but it is related to the development of a new kind of questionnaire. I don't know if there are people here interested in questionnaires and so on. And I do this with a student, a retired man that was working, who was working in the marketing sector, and who came to me, and so we developed this model together. And so we developed a causal model based on the notion of product value. Product value means how much do you like this kind of product on a scale from 0 to 10, right? And we then try to find out what are the reasons why that person says that he or she likes that music so much. The theoretical model is a causal model. The underlying statistics is done with the structural equation modeling. So this is, but I don't go into details, but this is actually the same model in different degrees of complexity. So we have the music piece. It generates an effect in the mediator, and so we here can assess the levels of arousal, of dopamine that the music generates. And these two sides, here we get answers to questionnaires, and also here questionnaires. So this part is, let's say, the causal part, and the measurements via neurobiology, basically. This part is more the survey part. And so each block can be seen as a kind of latent source where we try to identify the latent variable via a larger set of questions here, and here it's measurements of the body, basically. Also there large question. And so the structural equation modeling is a combination of factor analysis and regression analysis. So the regression analysis is when we link the latent variables together. Just to give you an example of an experiment that we did in the opera in Ghent. The opera wanted to know if it makes sense that they give an introduction to the audience before the opera starts. Right? Because that's a big effort for them, and so they want to know if it has an effect on people. So what we found out here is that the people that have no intro have a higher appreciation of the opera than the people that got the introduction. Of course, it all depends on the kind of introduction that you got. So this was done by a person, okay, a video, and so we say that it's that person's effect that we have here. But okay, the thing is that we have here the appreciation, and then here we can see the aggregates that contribute to that decision. It's just an example. Today we are asked by the Belgian radio company to work together for the top 100 classics. They have 28,000 pieces of music, they have 4,000 participants, and so on. And we are going to set up, let's say, a questionnaire for them and try to find out why people would choose the top classical pieces that they choose. So that's very different from what I was talking about before, but it's also a point of interest. So the conclusion is that the nature of our data are multimedial, because we use audio, motion capture, e.g. sensors, also multimodal, because we work with auditory thing, with body movement, with brain activity, questionnaires, so different modalities, and also multivariate, because even a single thing like body movement has many time series evolving at the same time. And so that's my basic statement, is that data analysis in our field requires good knowledge of the theory-driven research question. But of course we are in the need of very advanced methods to really be able to manage this very complex data set. And I thank you very much for your attention.
Some comments, questions? Okay, I think we have presented a very nice collection of data, of research questions that you do. So I think statistician or our research on complex model, with functional data, spatial data, can be applied successfully to solve some of your research questions. Some papers that we have made with Marc as an example of them. In some weeks, Marc is going to give a talk, a more mathematical talk on this paper. So, thank you again for your presentation.
I avoided talking about Marc's data because he should do it by himself. So.
Okay, thank you.
Thank you.